I'm a third-year grad student here at UC Santa Cruz, and today I'll be talking about using fast radio bursts as probes of extragalactic magnetic fields. And here are some of my collaborators that I worked with on this project, paper coming soon. I don't think that, oh, there it is. So one of the main motivations for this project is characterizing magnetic fields of normal galaxies using fast radio burst properties. And I'll, I guess, kind of show you what normal means. Oops, there we go. So one thing that we try to do is constrain the underlying physics of magnetic field production and amplification in Milky Way-like galaxies. We compare our measurements of rotation measures to those that are simulated in galaxies in the Auriga project, which is a magneto-hydrodynamic cosmological zoom simulation of galaxies. Here are 3 shown that were taken from these simulations presented in Packmore et al. 2018. And that's a face-on view of the host and then an edge-on view shown on the bottom with this rotation measure map color-coded from like negative values to positive there on the right. So yeah. Measuring magnetic fields in general is pretty challenging. These are some of the ways that people go about doing that. The Zeeman effect, so looking at splitting in atomic levels and transitions, seeing how that makes itself known, I guess, in spectra of galaxies or various locations in the galaxies. We also look at synchrotron emission, so that's, as the electron is accelerating along a magnetic field, and the radiation that is produced during that process, and then also the polarization of light. And that's the thing that we are focusing on here. There we go. So polarization just pretty much means that the direction of the oscillations in the electric field are well defined. Otherwise, you have this sort of like these random orientations. It goes through some polarizer, and this wave, for example, is linearly polarized. So we have this well-defined direction of oscillation. And FRBs are polarized emission. And then the Faraday effect is the effect of some magnetized plasma on that linearly polarized light. So we have our polarized light. It travels through some medium, in this case a magnetized plasma that has a magnetic field that is parallel to the direction of propagation, and then that induces a sort of rotation of that angle of, what is it called, polarization. There we go. And then the measure of that rotation is what we call the rotation measure. And that can also be defined as an integrated quantity along that line of sight that takes into account the density of electrons, the magnitude of the magnetic field that's parallel to the direction of propagation, as well as redshift. So for our FRB rotation measures, we can measure that angle of rotation as a function of frequency, and then use that to constrain the strength of the magnetic fields that our burst signal is interacting with on its way to us. And the FRB signal has a lot of information encoded in it. One property is the dispersion measure, which is pretty much this sweep that is caused by the different velocities at which different frequencies move through the ionized medium that it travels through, such as the intergalactic medium, our own halo, things like that. And you have frequencies arriving to your detector at different times, and that kind of spread in the time can tell you about the density of material that it traveled through on its way to us. Then we also have the rotation measure, as I said, derived from the polarization signals of the FRBs. And these Stokes parameters are measured, and then we are able to derive the rotation measure from there. And then taking a ratio between the rotation measure and the dispersion measure allow us to compute the magnetic field. We take this ratio, they're both these integrated quantities that take into account the density of electrons in ionized material. They cancel out, assuming our B field is positive, and then we get something that looks like that. So we're able to take a closer look at the magnetic fields of FRB host galaxies, mostly right at the location of the FRB. So looking at its immediate environment, but also what magnetic fields are kind of greater than that too, or along that line of sight that the FRB traveled through. So the main point of our investigation, we want to infer the magnitudes of galactic magnetic fields of these galaxies that are at a redshift less than 0.5. Questions that we want to focus on: what is the typical magnetic field strength indicated by the FRB rotation measures? And do we see trends with magnetic field strengths and other galaxy characteristics? And also, how do the rotation measures of these galaxies compare to those predicted by magnetohydrodynamic simulations? So here are some plots that kind of describe our sample. We have mass and star formation rate, and then a color magnitude diagram over here. And this sample is mostly represented by star-forming galaxies. Some are kind of transitioning, and then two are in this kind of quiescent cloud. The gray and blackish that you see in the background is a 2D histogram of hosts in the PREMIS survey. And then over here as well, some are in this blue cloud, some are in the kind of green valley, and then one kind of squarely in that red cloud up there, so quiescent. And then taking a look at these plots, here we have redshift and dispersion measure, and then redshift and rotation measure. With dispersion measure, we see a very clear redshift dependence in the sort of extragalactic contribution to the total dispersion measure of the FRBs, whereas with rotation measure, we don't see very much Z dependence. So this tells us that our rotation measure is mostly due to the host contribution. We're not really being affected very much by intergalactic magnetic fields, and we're also able to subtract off the magnetic or the rotation measure contributions from the Milky Way as well through various models that map the sort of rotation measure sky of the Milky Way. So as we search for correlations between other host galaxy characteristics or local environment characteristics and rotation measure, we find that there are very strong correlations between rotation measure and DM host, and rotation measure and the host normalized offset. And the stars just tell you that there is a correlation, and this empty star says there's an anti-correlation between the two. So we see RM and DM host, and this positive correlation that I stated before, and then rotation measure and host normalized offset shows this anti-correlation here. And I think this kind of further supports the association of the rotation measure signal with kind of mostly coming from the host that the burst is originating from within. Yeah. And I guess a little bit of context for the DM host estimate here. We use what's predicted by the McCourt relation, which I showed that DMZ relation prior. So here we're looking at rotation measure as a function of or compared to DM host. Our points are measured values for the FRBs in our sample. This little cartoon line is just a visualization of what the value is for our local solar neighborhood, which is 6 microgauss. The top line is 10 microgauss. This middle line is a constant magnetic field of 5 microgauss, and then the bottom one is 1. And we see that most of our points, most of these FRBs, are in environments that are a bit lower than that 5 microgauss level. So yes, I guess environments don't quite look like what we see for the solar neighborhood, but this could be due, I guess, to various kinds of effects. So I can go into more detail. And then we also take a look at how this compares to simulations. So this just shows rotation measure and dispersion measure on log-log scale. And we see a very strong correlation between rotation and dispersion measures in the simulation itself. And then here we show PDFs for rotation measure and dispersion measures as predicted by the simulations. In pink is the dispersion measure, purple is rotation measure. And with these predictions, our measured values are these vertical lines that you can see. And then we have this dashed yellow line that's described here, where we set a limit on the dispersion measure, that is based on the measured value of the dispersion measure that we have for the burst. So we set some upper limit of 2 times the observed dispersion measure. And with that limit, we're better able to predict or recreate the observed values of the rotation measure. And without that limit, we kind of select for sightlines or get predictions that are a bit higher than the actual rotation measure values, or even a bit lower. And I want to focus specifically on this one up here. So this is the predictions for this burst 2012-1102. This was one of the first bursts that was localized to sub-arc second precision, and it was localized to a dwarf star-forming galaxy, to a region of enhanced star formation in its galaxy. And if we can see here, for both the DM limited and the not limited rotation measure predictions, we underpredict the rotation measure for this burst. And I think that's interesting for this case in particular, because this shows evidence of this really highly magnetized environment that the FRB progenitor is within. So even when our predictions don't quite match up between the simulations and then our observed measures, we can see that that can still tell us something about the local environment that the FRB progenitors are within. So just to leave you with these, we can use FRBs to probe galactic magnetic fields. It also seems in these simulations that there's a strong correlation, and also in our observations, a strong correlation between rotation measure and dispersion measure. But with rotation measure, there's not as much of a strong redshift dependence. And then these simulations can very well reproduce the observed rotation measures, but we can also use the rotation measure to learn more about this magneto-ionic environment around the FRB progenitors. And that's it.
Thank you, Alexandra. We have time for questions. Actually, can I ask to clarify, maybe I missed a step on your main plot here. You're showing the observed rotation dispersion measures, and then the curves show the predictions from the simulations.
Yes.
How are they different? Like, is it the viewing angle? Is it the exact simulations you choose to overplot there?
The different
predictions. What's different between? Are you looking at different galaxies? It looks like you're combining the different galaxy simulations.
Yes. Sorry. So each of these is a different galaxy that we modeled and then picked out that had similar, like, stellar mass, star formation rate to what's measured for the host galaxies that the FRBs are in. Yeah.
Hello. So what are the prospects of you increasing your sample size in the future?
That's a great question. So there are a number of surveys, I guess they're about to come online in the next year or 2 or 3, that will greatly increase the number of FRBs being detected and localized every year. So the prospects are very good. I think by the end of the year, a survey called Krakow will hopefully turn on, and then we'll get a higher number of highly local, or precisely rather, localized FRBs, and then we can do a lot more of this sort of stuff because we'll have dispersion measures, rotation measures, and locations to look at their host galaxies.
All right, thanks for the talk. This is a naive question. So from the plot you're showing on the upper left corner, it seems that the magnetic field strengths of your different galaxies in the sample are quite different, right? Mm-hmm. They have a decent scatter. And I was wondering how big this scatter compares to like the degree of your of the magnetic strength varies within the extent of a single galaxy. So if you have multiple like FRBs within a certain galaxy, then you're measuring the magnetic field through multiple sight lines. All right, so I would suppose that I would presume that the strength you get from each sight line would be a bit different. And how does that variance across different sight lines compare to the scatter between different galaxies?
That is a great question. So for most of these FRBs, there's just a single sight line like through each of the galaxies. So as we get more bursts that might intervene with, you know, a single galaxy more and more, then I think we could say more about that. At this point, maybe the thing would be to use like other sources of kind of short duration, like radio emission, that we could also get rotation and dispersion measures for that are not FRBs, to kind of try to do that. Or so other ways, I guess, of making these rotation measure maps that can tell us about but in the simulations themselves, right, they can range from like a few to tens of microgauss. So I think, we need a bit more data to say more about how the observations kind of trace that. Yeah.
Hi. Thanks for a very nice talk. Point of clarification, and I just to make sure I understand, you do find, or I mean, it has been found a strong intergalactic contribution to the dispersion measure from free electrons in the cosmic web for the most part, but not so according to what you're showing in the rotation measure. Do I interpret from that the ratio of the typical magnetic field in a galaxy versus in cosmic filaments, for example, is dramatically higher than the typical ratio of the electron density in a galaxy versus cosmic filaments?
I guess so, yeah.
Okay.
Yeah, I'm not, I guess, I don't have very much confidence in saying yes to that, but that sounds like,
And then I wonder if that could be used to constrain models of growth of galactic magnetic, like turbulent dynamo models or things of that sort.
Yeah, I think that's the idea.
Thanks.
Okay, let's thank Alexandra again.
Okay, so this is the beginning of the afternoon break. Before you get goodies, go out and stand on the steps for our group photograph, okay? Then it'll only take 5 minutes, then lots of times for goodies and discussion.